Differential equation for heat conduction. Consider a general situation where the temperature T of a substance is a function of the time t and of the spatial coordinate z. The density of the substance is ρ, its specific heat per unit mass is C, and its thermal conductivity is kappa. By macroscopic reasoning similar to that used in deriving the diffusion equation, obtain the general partial differential equation which must be satisfied by the temperature, which is now time dependent and has spatial dependence. So we have the temperature T, which for a substance with density ρ, specific heat per unit mass C, thermal conductivity kappa. Now, if I consider a plane for z is equal to constant on this substance, there is the heat flux entering this region between z and z plus dz, that is q of z, and there is the heat outflux, basically q of z plus dz. So I call q the heat and this funny q the heat flux density or heat flux. Now, what is the heat transmitted? It is mass times specific heat per unit mass, C, which gives us the heat capacity, mc, multiplied by delta T. Now, what is the mass of this substance? Mass is its density ρ multiplied by the volume dV. Well, what is the volume dV? The volume dV of this region is its cross-sectional area A multiplied by the height dz. So volume dV is A dz, and therefore we find that mass is equal to ρ A dz. So if I substitute that here, the heat Q is ρ A dz multiplied by specific heat per unit mass multiplied by delta T. Now, this is the heat that is being transmitted through this region due to the temperature differential between Z and Z plus dC. If I look at the time dependence of this heat, the increase in heat per unit time in the volume A dz, dq dt, that heat transmitted will increase in time due to the heat flux entering this region at Z minus the heat flux leaving this region at Z plus dZ. So heat flux multiplied by the area gives me the heat per time, the heat flowing per time. Now, what is dq dt? If you look at this equation, A, dz, and rho c are constant, so it is due to a change in the temperature in time. So this is rho A dz c del t temperature del t time. So you can see in this equation the areas will cancel, and I will be left with rho c del t del t. This dz will go downstairs to the left hand side. So I will have rho c del t temperature del t time is equal to, now heat is entering at z, leaving at z plus dz. So with a minus sign here, I will have the heat flux at z plus dz, leaving minus the heat flux entering at z divided by dz, and I will consider this in the limit dz goes to 0, so that this will give me rho c del t is equal to minus del heat flux del z. Now heat flux is related to the temperature gradient as minus thermal conductivity del T del Z. This is the law of thermal conduction here. So if I substitute that to this equation, rho C del T temperature del T is equal to, now I have two minus signs, they become plus. So I have minus del Z of minus kappa del T del Z. So this gives me the second derivative. Now putting rho and C to the bottom on the right hand side, I obtain the time derivative of temperature del T is equal to thermal conductivity kappa divided by density times heat capacity per mass multiplied by del square T del Z square. So this is the equation for a differential equation for heat conduction, which is similar to the diffusion equation. So we have used the same situation. So we can say that this is like the heat diffusion equation. Okay, so we're looking at a general situation where the temperature is time dependent across a substance, so that we want to calculate, we want to reach the differential, most general form of the differential equation for heat conduction, knowing the temperature, density, specific heat per unit mass, and thermal conductivity. Heat is entering this region between Z plus dZ at Z and leaving at Z plus dZ. So heat is flowing up like this, let's say, and the heat that is being transmitted in this region is mc delta T, heat capacity times delta T. M is density times dV, the volume of this region, which is the cross-sectional area A multiplied by dZ. So we can see that this is a plane that has a cross-sectional area A. So if you want to think in 3 dimensions, this would be basically this area A here. The same thing here. We have this plane that has area A. Now this heat flux, which is the heat flowing per area per unit time, is this funny Q, heat flux density. And you can see that the heat being transmitted is m, which is rho a dz c delta t. If you look at del q del t, time derivative of the heat being transmitted, it is due to the time derivative of the temperature, del t del t. But what is the heat that is being transmitted through this region? It's the heat flux entering minus the heat flux leaving multiplied by the cross-sectional area A. And the A's will cancel, and if I take this dz to the left hand side with a minus sign here, I realize that if I change this order, I obtain the definition of the derivative, del heat flux del Z. So for heat flux, I substitute the law of thermal conduction minus kappa del T del Z, and this gives me a second derivative for the temperature. So final answer is del T. Temperature with respect to time derivative is kappa thermal conductivity divided by density multiplied by specific heat per mass del square T del Z square.